Hi everyone, in today's video we are going to be covering the topic of a rapid solution for a simple truss structure. This method basically covers, it is what it sounds like. It goes through a quick way to solve a simple truss structure. Many of you may be familiar with the method of joints or the method of sections, and although those methods are very simple, easy to use in terms of breaking down a truss structure, they do a very thorough job and you're able to analyze each point and solve it for what you need. Sometimes solving truss structures is quite time consuming, and this is a easy way to solve them quickly. So if you have something like this on like a test, you can solve it quickly. This was something that was taught to me by a TA of mine, and I found it really helpful. And I thought I would share this knowledge because I haven't seen many videos for it on YouTube. So I wanted to pass that along. So first we're going to go through some key assumptions and then I'll get into the procedure. I already wrote out these assumptions here, so we don't really have to worry too much about me taking extra time to write them down. I want to try to keep this video as short as possible because I know that going through the explanation for how to do this simple truss solution is quite long, but once you get really fast at it, it'll actually be a lot shorter than what you think, but it does take quite a while to explain, so that's unfortunate. Anyway, I'm going to stop rambling and get into it. So our first assumption we have here is that the structure we're solving for must have horizontal and parallel top and bottom chords. The second assumption is that there must be a repeating internal web geometry in this structure. There must be 2 members per repeating cell, which is our third assumption. And you can see in the diagram I drew below, it's not a very good diagram, but it is a diagram nonetheless. You can see that the 2 repeating members in this example truss structure are highlighted in blue. So we have the one that's diagonal and the one that's vertical. Moving on to our fourth assumption. Our fourth assumption is that the member signs can be correctly and hopefully easily assumed, because again, this is a simple structure. We shouldn't be spending too much time assuming what the member signs are. It should be like a structure in which we can correctly and quickly identify them. And then our fifth and final assumption is that vertical applied loads are the only kind of loads that are allowed in this structure. And again, as you can see, I've drawn some little red arrows in the structure below, and those arrows indicate the vertical applied loads. Alright, so now that those assumptions are out of the way, let's move on to the procedure. I'm just going to outline the procedure in a series of steps, and then I will go into what occurs during each step in more detail and hopefully provide an example. So the procedure, here we go, procedure. Ooh, that's a little spaced out, sorry. Procedure, okay, let's underline this. So step 1, there are 3 steps to this procedure, and the first step is that we are going to assign member signs to all members. So remember that we have a negative sign for compression and a positive sign for tension. Alright, moving on, that's our first step. Our second step is that we are going to calculate the vertical force distribution and solve for all web member forces from geometry. Okay, that may sound a little confusing now, but again, I'm gonna go and explain this step and the other steps in more detail, so don't worry right now. And our third and final step is that from the web forces, we're going to sum to find all of the chord forces. Okay, so that is our procedure. Those are our 3 steps. Again, you may be a little confused right now. That's totally okay. I think I was a little confused when I learned this for the first time because just looking at these steps, they don't really exactly tell you what you're doing. But once you start to actually use this method and understand it in more detail, it is actually quite simple. Okay, so step 1. In more detail now. Member signs. Okay, so for a standard truss bridge like the one I showed above, the top chord tends to be in compression, which, if we recall, compression is denoted by the negative sign. And then if the top chord tends to be in compression, the bottom chord tends to be in tension, which, again, if we recall, denoted by the plus or positive sign. And web forces alternate signs, so they alternate from positive to negative signs, or plus or minus signs. And we want to use the diagonal over the support to find the pattern. Okay, so an example of this is, say we have a truss bridge that looks something like, actually this is way too big. Let's draw a smaller one. Say we have a truss bridge that looks something like this. If we have the structure, oops, okay, I'm gonna redraw this one more time. Okay, here we go. This looks a little better. Okay. Not perfect, but it is what it is. Okay. Again, not perfect, but it's okay. Okay, so we said that the top chords tend to be in compression. So we would denote these top chords with a negative sign. Gonna put that all in blue. And then our pattern for our diagonals, not all in blue, I'm gonna put that all in red. All the compression is gonna be in red, sorry, and then our tension will be in blue. So compression is red. Yes, so then our diagonal pattern is going to be negative, positive, and then negative, positive, and then again we have negative, and then positive. I'm just gonna, instead of drawing this in, I'm just gonna put the red and the blue. I'm getting a little tired of writing it all out. Actually, no, wait, I'll do it. I won't be lazy. And then here at the center line of your truss bridge, pattern is going to swap, so it's going to be negative, positive, negative, oops, positive, and then negative. I also denoted the center line with this symbol, CL, for center line, which is just the part in the truss structure that is the same as the other half. And what we're doing when we're solving in this process, we're only going to be solving for one half and then basically flipping our values as like a mirror image on the other side. So that's what you're doing. If you only want to label one half, when you flip the mirror image, make sure you're flipping correctly. So that's basically what I was trying to get at earlier. I don't know if my explanation there made much sense because it's a little bit difficult to articulate, but basically that's what you're doing. Anyway, on to step 2. Okay, step 2. And in step 2, we are dealing with the vertical forces. And we want to set the sum of all forces in the y direction to be 0. Okay. And this is because we're doing this because the chords are horizontal. And because the chords are horizontal, we have vertical forces in only our webs. So vertical forces are in the webs only. Gonna circle this. Only. A little bit of excessive circling, but yes, only in the webs. So in my example truss bridge here, okay, again, not exactly perfect. Let's assume that these are equilateral triangles, and let us make this the center point. So let's say that there is some center point here, some center line. So this is only half of the bridge. Center line. Let's assume that we have an upwards force of 2.5 P, and then a downwards applied load of P at this joint, another downwards applied load of P at this joint, and then actually I'm going to move this over a little bit. Make this our center line. So this is our center line. Sorry about that. And then we're going to have a downwards applied load of P over 2. And the reason this is P over 2 is because it is only half of the applied load, because this is half of the bridge. If I were to draw out the whole thing, there would be, if I were to draw out the whole structure like this, there would be applied load of P at each joint, but I'm not doing that, so don't worry. It's P over 2 because it's the center line, and we must take half of the applied load. So I would like to also say that from geometry, the diagonal and horizontal components in the web can be solved once the vertical component is known, and that's why we are considering this. Okay, so what we want to do is we want to kind of set up this little staircase of what is happening to the forces over time as we go from joint to joint. So we start off with 2.5 P of an upward force, but then as we move to this joint, because this forces acting in an opposite direction, and this is assuming that the positive direction is up, we are subtracting P from this. So then our value drops to 1.5P. We subtract another value of P from this, it decreases to 0.5P, and then once we get to our P over 2, it goes to 0. So this is what basically happens to our forces over time. This is 0, so it doesn't count. So this is like a little staircase that represents what is happening from joint to joint. And this is what we want to do when we have an actual bridge that we are trying to solve. We're going to want to, instead of using P, we might have some upwards force and then our applied force, and we'll be subtracting that amount each time. And you'll see that when I go through an actual example. Okay, moving on to our third and final step. Step 3, which is chord forces. Chord forces. And this is where the sum of all forces in the x direction is equal to 0. Okay, so it is important to note that the horizontal component in the webs increases the magnitude of the chord forces as you move towards the middle of the truss structure. As you move, I can't spell, sorry, it's a simple word, what am I doing? Move toward the middle of the truss structure. So here we have the top chord, I'm just going to draw it out. Top chord. So we have some joint here. We have force 1, force 2, force 3, and this is the force in this chord. So F4, or this is just, we want to find the force in this chord, in F4. So basically what F4 would be is, well, before we determine what F4 would be, we need to assume that F1 and the web forces, which are F2 and F3, are known. But if we do know what they are, and we want to find out what the next chord over is, which is F4, we can basically say that F4 is equal to F1 plus F2x plus F3x. And if we assume the same thing for the bottom chord, which looks something like this, say we have F5, we have F6, we have F7, F7, and then we want to find the value of this chord, which is F8. So the next, again, assuming this is the next chord over, and we've already solved for F5, F6, and F7, these are known. Then we could say that F8 is determined by the sum of F5 plus F6x plus F7x. Okay, and note when we are using these equations, we are only subbing in the magnitudes of the forces. We are not subbing in anything to do with whether they are in tension or in compression in terms of the signs. We're only subbing in the magnitudes. So I just thought I would note that. And I didn't label this, but this is the bottom chord. Okay, so this is kind of the conclusion for the overview of the procedure. Now I'm going to kind of go into how you actually use these steps to solve the problem. Okay, so in this example problem, we are going to have a simple truss structure that looks something like this. Hopefully I can draw it semi-decently. Okay, sorry, this is going to take me a bit of time to draw. We want to have an applied load. Okay, I should denote the applied loads in red because that's what I've been doing. 10 kilonewtons. And the applied load is going to be the same at all of the joints. And I'm actually going to make this the center line. So this will be the center line. I'm going to make that blue. Oops. This is the center line. And one more. Okay, so this is all 10 kilonewtons at each spot here. I decided I'll write it out even though I didn't want to. I'm not going to be lazy. Kilonewtons. Okay, so now we want to find what. So our first step is to determine what the signs are. So our member signs. This is the bridge I actually used in my example, so we know that this is negative, 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 all on the top here. This is negative, this is negative, this is negative. All of our diagonals are also negative. Then we have positives here in our vertical portions. And I'm not sure if I'm going to actually go back to step 1 and check if I did this. I may have missed part. No, I missed labeling the bottom here. Yes, this should all be positive as well in our example that I missed in the first time I did this. Sorry, now I'm going to move back to our example, but yes, we should also label our bottom chords as positive. I'm sorry, I made a mistake. Okay, so our step 1 is complete. We've done this. Yay! Now, moving on to step 2. First, we want to take half of our bridge, because the way I'm solving, I like to only analyze half, and that's what works most efficiently in this method. So I'm going to calculate the reaction forces for the whole bridge first. So I have 10. Wait, before I get into that, I should also note that the dimensions of the bridge are 4, 3, and 5. Because this will be coming up during this step. So I have a force acting upward here, a force acting upward here, and then I have 1, 2, 3, 4, 5, 6, 7 forces acting downwards. So I will need a force of 35 kilonewtons, sorry, acting up at each joint. in order for this structure to stay up and not collapse. And we're assuming again that this both of these joints, because they're, you know, there's equal distance between both of these points, that they're going to be carrying the same load. So now, knowing this, we want to take our half of the bridge that we are going to solve, and we are going to make our little staircase thing that I was talking about earlier. So we start with our 35 kilonewtons, and then as we move from this joint to the next joint, we are going to be subtracting 10. So we have 25 kilonewtons. And then we're going to be subtracting another 10 as we move to the next joint. And then we have 15 kilonewtons as we move to the next joint, or from here to this joint, sorry. We're subtracting another 10, so we have 5 kilonewtons. And then once we finally get to the center line, which we should be assuming has a value of 10 kilonewtons divided by 2, we will arrive at 0. So this is our little staircase diagram. And now what we want to do with this staircase diagram, that I didn't really get into too much during my explanation of the second step because it's a little difficult to explain. But what we want to do is we want to create a chart now. And in this chart, we want to put all of our vertical forces. So at the top, so we have 35, 25, 15, and 5 at the top. So this is our V here. I'll make it more like a V. This here to represent our vertical forces. And then we want to also have another category in our chart called member type. And with our member type, we are going to draw out each of our members. So we have our first member type is our diagonal member, and our diagonal member has both a horizontal and a vertical component. Sorry, a horizontal and a diagonal component that we want to determine values for. We want to find the values for our horizontal and diagonal components. So we're going to be multiplying by 4 over 3 and 5 over 3, because again, if we go back to our little depiction, sorry, we can determine that that's what we would have to multiply our vertical component by to determine our values for our horizontal and our diagonal components. So I should probably write this out better. We should say V times that is equal to H, and V times this is equal to D. Okay, so now we're going to go through and fill in the chart. So if I take 35 and I multiply it by 4 over 3, I should get something around 46.7. I'm just kind of rounding. And then we're going to fill this in. I'm not going to go through every single value, but this is a rough approximation. I think I made a mistake. Sorry, this should be 20. And this is 58.3. This is 41.7, 25, and 8.3. Okay, so once we're done with that member type, we move on to our other member type, which is the vertical component, our vertical member. And here, our horizontal component, and then our vertical component, which is equal to our diagonal component, because there is no diagonal portion to this member, so all of its diagonal forces will be considered as its vertical forces. And since there is no horizontal component, this is all going to be filled in as 0. And then this will just be filled in as 35, 25, 15, and 5. Okay, sorry I zoomed out a little bit, but basically now that we've determined all of our forces and we've completed this chart, what we want to do is start on our third step, which is filling out our diagram with all the forces and summing our forces to determine the values of the forces in the chords. So what we would do is, I'm actually going to redraw the diagram because that might be simpler. Okay, I'll draw half of it actually, because we are really only considering half, because then the forces will swap and it'll be the same. Okay, I'm not very good at drawing. This truss unit has taught me that. But, okay, here we go. I think we have one more unit after this. It's 4 units, if I believe I'm correct. No, it is 3, I lied. Yes, okay. So what we would do here is we would look at our forces in our horizontal component, and we would start off, say we're considering the bottom chord. We will take our 46.7, that'll be the forces in this chord. Then we will take this and we're going to move over here, and we're going to add these two values together to get the value of our second chord. So 46.7 plus 33.3 is 80. So we're going to keep that value at 80, and then we're going to move over to our next chord and add 20. And once we do that, we're going to add 20, so we're going to get 100. And then we're going to move over to our last chord here. We're going to keep our value of 100, add 6.4, so it's going to be 106.4. And the same thing would go for the top. We would start with our 46.7. And then we'd add 33.3, we'd get 80, add 20, and get, add 20 and get 100. We should also note that these values are all in kilonewtons. But that is how we would solve for our chords. Then we would next want to go about our diagonals. So that's kind of the simple part. We look at this column to fill in our graph. Sorry, our diagram. We're gonna have our negative 58.3. Then we're going to have our negative 41.7, negative 25, and then negative 8.3. Again, these values are only considered negative, as that is what we denoted them to be with our sign convention. And I also added negatives to the top chords as I realized I forgot that, and I will now add positives to the bottom here. And then lastly, we're going to look at our column here for our vertical components, which we already know. It's also up here. Since we have zeros here, we don't really need to do anything, so we can disregard that. That was more for our intuitive nature to understand what we're doing. And yeah, so this is 35, 25, 15, and 5. These are all positive. And then one thing to note is this value of plus 5 would actually be plus 10, but since we're considering the center line, we're saying plus 5. Once you draw out your entire diagram, make sure to change this to whatever double the value is when you're solving for this portion of the bridge. But given our nature of our half bridge, I can't say that it's 10 because it would not make sense right now, logical sense, but that is something to note. And yeah, that is the solution to our truss structure. I know it might seem quite difficult to comprehend what just happened, but believe me, once you get into this method of just making this little step ladder thingy, don't know exactly what to call this, but once you get into the habit of drawing this out and then using some basically simple trig ratios to figure out what should be going into this chart, and then adding some values, it cuts down the time that is required to do method of joints or method of sections, because those methods take quite an amount of time. I also understand that this is not exactly the easiest method to explain verbally. It is something that is developed by doing. I might just post another tutorial of me solving, because it is, again, quite a difficult method to understand just verbally, and I don't know if I did it justice by explaining it the way that I did. So if you did not understand, please feel free, put a comment down below, let me know. I will be glad to answer your questions, go through another example if needed. But otherwise, I hoped that this helped, because this is a method that once you get the hang of it, was very helpful to me, and I enjoy using when I have to solve a simple truss structure, because it does save a lot of time. And I'm gonna stop talking now. I sound a bit like a broken record, and I will see you in the next video. Thank you for your support. Bye.